and today I'm going to talk about Monte Carlo methods. So I should have actually added this slide before the contents. What we saw last time, finally, was an algorithm which is viable for very large-scale problems. And the trick with SDDP was using Monte Carlo to deal with a large number of scenarios that can happen. And it's one of the things you could do with Monte Carlo. It's not the only approach you could use. So what I'm going to show you today are a couple of different variants that are all inspired by simulation. So there's a couple of different variations, and we'll see them today. So what we're going to see in particular is sample average approximation, which, if I'm not mistaken, was, if not proposed by Shapiro, definitely analyzed by Shapiro. Then an idea based on importance sampling, which was proposed, or at least Jared Dinfanger worked on it a lot when he was with George Danzig at Stanford. And then we'll see how these two methods compare on a specific example that's in the book. And finally, we'll talk a bit about scenario selection. Okay, so what do these things look like that we're going to see today? Three approaches we're going to look at. Sample average approximation, an idea based on importance sampling, and scenario selection. The sample average approximation algorithm looks as follows. You just simulate a bunch of scenarios in advance and use them as fixed input for your optimization. So these things are supposed to represent time series of uncertain input, for example, in your problem, and then you fix that input. The way you simulate this uncertainty is using the uncertainty model that's been handed to you by whoever posed the problem. You independently generate a bunch of outcomes, and you optimize your problem based on that input, and that gives you a solution X star. That's sample average approximation. And if you think about it, it's quite simplistic. The way it approaches the problem, it just pulls a large number of independent outcomes from the source of uncertainty. Now, you can become more fancy about sample average approximation and do it in a sequential fashion where you simulate, you optimize, you generate a cut, and then you erase your original sample and re-simulate, re-optimize, generate a new cut. So that's a sequential version of the problem, of the algorithm. And then there's an even fancier version of that where before simulating, you change the probability distribution that you use to pull out the samples so that you focus on the more important samples, and we'll see how that's achieved through importance sampling. So these are the three main algorithms that we will focus on today, and let's jump to the first one. Okay, this is, for me, the easiest way to visualize why Monte Carlo is useful, and we've seen this in previous slides. So expectation is something you can't escape when you're doing stochastic programming. And there's two ways to do it. Like we saw, we can do enumeration or we can do simulation. When you do enumeration, you basically look at your random space, which in this case happens to be two-dimensional. You have to go one by one on each possible combination of outcomes, compute their cost for that x, and then evaluate the value function. Now, if this is not two-dimensional but 2,000-dimensional, you have a problem. That's too many combinations. Whereas with Monte Carlo, you can just pick a few of these boxes and get away with an approximation of the value function, but at least you control the number of optimizations you need to do. So these are the ones that are hurting us. It's that once we pick a sample, we need to run a linear program. So we're trying to control the size of the number of times we have to do this. So in this case here, we ended up randomly, and we happened to pick 0, 1, 1, 0, 1, and we used their average with a weight of 1/3 as an estimate of our value function. Now, this idea is applied in sample average approximation. So instead of optimizing the true value function v of x here, we optimize an estimate of that value function for a finite number of samples, little v. Okay, so you should be thinking here situations where you're not given a scenario tree. Someone just walks up to you and tells you, here's how the uncertainty looks like. For example, what happened in the project. I never told you how to build your model of uncertainty. I just gave you a time series model for wind production, and you can do whatever you like with it. That's the idea. So in sample average approximation, we pull independent samples of the uncertainty, psi k, and we replace the v of x with this estimate here, which means that in extended form, we're now solving this problem here. So what's changed compared to what we've seen in the usual L-shaped method is the probability weights, right? So now we have an equal weight on each of the independent samples that we happen to pull out. And I should actually have little v here instead of capital K. Since we're pulling little v samples, I'll fix that and upload the new version. Okay, so what guarantees do we have about this? Okay, yeah, here's a schematic. First we simulate, then we use that as input for an optimization, and once we were done with the optimization, that's the end of the algorithm. We throw the X star back to the user, and we report this as the optimal thing to do. So what guarantees do we have about... Here we're not solving the real problem, if you think about it, right? The real source of uncertainty is the distribution that we're pulling samples from. Intuitively, what do you think will happen? Ideally, what would you like to do with this Monte Carlo idea? When would you get really close to the true optimum? In the project, for example, ideally, which stochastic program would you like to solve in particular? Do you want to run the wind routine 5 times or 5 million times? Obviously, the more the better, because the estimate of the value function is closer. So it makes intuitive sense that if you increase substantially the number of samples that you're optimizing against, that optimization problem for V going to, well, capital K going to infinity will look very, very much like the original true problem, right? And if the actual optimization problem looks a lot like the true problem, then the X star also looks a lot like the true X star. Okay, that's the idea. Again, it's a different problem if you think about it. If I replaced here this term with the true transition probabilities, that's one problem. Whereas if I'm replacing with a bunch of Monte Carlo samples, something different. But asymptotically, it's the same problem. Okay. So that's the guarantees basically we have, and don't worry, you don't need to memorize this theorem or prove it. It's just there for its two conclusions. So what the theorem says is that if we're looking at a two-stage stochastic program with a distribution, with a second stage cost g that depends on x and y. See, this is what we've seen already so far in the course. It's just more generally stated for nonlinear programs instead of linear programs. What the theorem says is that if we can upper bound the cost for every scenario and for every first stage decision, and if the moment generating function is also bounded, then we have a guarantee that the chances of our performance of the objective function value of the approximate problem, the SAA problem, being bigger, being out of a sphere around the true objective function value, the chances of this happening decrease exponentially with the number of samples that we're using. Okay, so again, the approximate problem, the chances of its objective function value being more than epsilon away from the true objective function value of the problem, the chances of that occurring decrease exponentially with the number of samples that we're pulling. And also the chances of the actual vector that we provide as an answer being more than epsilon away from the true optimum decrease exponentially with the number of samples. So that's the guarantees that sample average approximation can give us, and the way you would implement it in code is all you do is full stop. That's SAA. That's the first algorithm that we wanted to see today. And now I'm going to show you two sequential versions where we erase the samples and we regenerate them. Okay. Okay. The reason we were even going to consider sequential versions is that they can actually get even closer to the true optimum than just the simple SAA. So the first sequential algorithm that's inspired by sample average approximation is doing sample average approximation but throwing away our previous samples. So here what we're looking at is an algorithm where it's an iterative algorithm, and at each iteration we have a bunch of feasibility cuts and optimality cuts. We do the same thing we did with SAA, we generate V independent samples, and we solve for each of these independent samples in the second stage. That gives us a subgradient, and it also gives us the true objective function value for that sample. And if it's infeasible for the second stage, then we generate a feasibility cut. Otherwise, we gather this output, the Q's and the subgradients, and we generate the following optimality cut. So here's the recipe for the optimality cut. The capital E matrix is minus the subgradient. The little e matrix is this thing here. And I will justify to you in a minute why this is the recipe you should be using. Now, a couple of things to note here. Usually, you've seen so far in the course, the pi, we use it for the dual multipliers of the second stage problem. Here in the book, I'm following the notation of the book, it's actually the subgradient. These two are different, if you remember. How do they relate? So, what we've used in the course so far is the pi as the dual multipliers of this. But in the book now it's saying pi will be the subgradient of this problem with respect to Q. Do you remember how the subgradient relates to pi? There was this theorem we had, a generic result where we said that the subgradient of this function with respect to B are the dual optimal multipliers here. So in this case here, if we pull h minus tx and consider it as a right-hand side, the subgradient of this q function with respect to x is minus b pi transpose t. Okay. Okay, so the pi you're seeing there is minus pi transpose t, where pi are the dual multipliers here. Okay, so if you were to implement this in Ample and you went and plugged in these recipes pi as the dual optimal multipliers of these constraints you're getting here, it's gonna, the dimensions won't even be right. So keep an eye on that. Now, the other thing I wanted to emphasize is that this looks it looks like the L-shaped algorithm. It's just that we're doing simulation instead of exact enumeration, but it's slightly different, right? Because in these cuts here, we're not using the H vector, which in the L-shaped method, we're using it for the little e. So it's a different thing. It's a different, it's very similar to the L-shaped method, but it's a different philosophy of approaching the problem. And here's what it looks like again. So first, we simulate a bunch of things that could happen. We optimize for those things, and we generate cuts. In SAA, we would just run this until convergence and report the x as the optimal. Here, we're going to do something different. We're going to generate cuts based on this sample, and then we're going to erase this sample and create a new one and generate new cuts. And we're going to do that a bunch of times until convergence. Okay. So this is so what I want to focus your attention on now is what these cuts look like. How do they compare to the real cuts of the true problem? And to do this, well, before that, let me motivate the recipe I showed you for generating the optimality cut. So if you remember when we were doing the Boyd slides, on subgradients, we had this result that said that if I have a function that depends on some x and the random input u, and I have an f of x, which is the expectation of this f of x u, then I can compute subgradients of f by taking the expectation of the subgradients of f of x of u with respect to x. Okay? And so this is the result that was stated in Boyd. If G is if GU is a subgradient of f at a certain point x for a sample u, then if I take the average of that, that's a subgradient of f of x. Now, this idea builds the basis for approximating the subgradient of a function. So, how would you do a Monte Carlo approximation of f of x for a given x? You would pull out a bunch of independent samples of u and average it. And you would say, here's an estimate of f of x. Well, in the same way, you can provide an estimate of the subgradient of f of x using this result. You generate a bunch of independent samples of u, you compute their subgradient at a certain x, you average them, and you report this as an estimate of the subgradient of f of x. So that's basically the justification we're using for the cuts I showed you earlier. And so the cuts, if you plug in the cuts I showed you earlier over here, the recipe I gave you was, this is the optimality cut, this is the capital E, this is the little e. That's the recipe I gave you for computing the cuts. So if you plug that into here, you will get something that looks like this. So why is this the right cut to provide? Well, let's think of what guarantees the central limit theorem gives us. So if you're completely lost, because just let me know, interrupt me, ask questions, just in case you lost me like 5 or 6 slides ago. But if not, I continue. So I take the silence as a recommendation to continue. Okay, so central limit theorem says this term, if I increase asymptotically the number of samples, will converge to the true value function at xs. So we get this result here, and from the previous slide I showed you this thing, which is the subgradient of the Q function for a given scenario. As I increase asymptotically the number of outcomes, again according to the central limit theorem, will converge to the subgradient of the value function at xs. It will converge to this vector here. So this whole term here will converge to subgradient of V at xs transpose x minus xs. Okay. So if we apply the central limit theorem here to the entire right-hand side, what we get is basically this random variable here, which converges to a normal random variable. And this normal random variable has this average. And this average is the exact cut at xs. So what I've argued here is that the recipe I gave you asymptotically is the right recipe. If you had 1,000,000 samples and you used this recipe, although you, for example, in this recipe I gave you, for example, you never used the H vector, but asymptotically it would be the same as the cut you would get with the L-shaped algorithm. So that's the justification. Asymptotically, what you get here is a right-hand side that looks like this. It has a bunch of noise. This noise is Gaussian, but on average it's right. Its average is 0, and it has a certain variance. And here's what happens schematically with this algorithm. The red is the true value function. It happens to be flat around x equals 0. And now this, each iteration, this algorithm will throw the dice, pick a bunch of samples of uncertainty, and generate optimality cut based on these samples. These optimality cuts will have noise both on this term here, so on the estimate of the value function at xs, there will be Gaussian noise there, and there will be also Gaussian noise at the slope. So what you're going to get is something like the blue cuts here. You'll have some noise exactly at the point where you're approximating the value function, and then also the slope will be a bit unpredictable. It'll be centered around the true value at x equals 0, and it will be centered around the slope of 0, but there will be Gaussian noise around both of these two things. Okay. Now, the problem with this is that you basically accumulate bias. So if you continue doing this algorithm over and over, can you think of one bad thing that can happen? And this has to do with how we describe the relaxation of the true optimization problem using optimality cuts that are greater than or equal constraints. So, for example, this cut here is really off. Can happen. With the algorithm I propose to you, you're going to keep that cut. So for this part, the region over here, you're overestimating the true V of x. And that's not going to go away. You're going to keep that cut until the end of the algorithm. Now, you could argue back that, well, you know, it's an unlikely cut, and for example, you have all of these cuts that are underneath, so no big deal. But what I'm going to answer back to you is that, yeah, but in your relaxation of the problem, you have theta greater than or equal to all of these guys, including the worst one. So this theta greater than or equal to something noisy is creating a bias. because when you were approximating x at 0, you happened to screw up on the left side of x, and this propagates until the end of the left-hand side axis. But then you might then try again to approximate around x equals 0, and you might generate this cut here. And this one is going to overestimate the value function on the right-hand side. So again, because of this theta greater than or equal to something, and because the something is something noisy, you create bias. And you end up, if you're iterating this algorithm too many times, you end up over-approximating your value function. So here's in drawing what I'm trying to say in words. You basically have a true value function, which is a solid black line. At x1, you might generate a noisy cut like this one, where note that the dot is slightly off from the true value function, and also the slope is slightly off. And the problem is that this cut over-approximates the value function for these x's over here. Then at iteration 2, you might generate this cut here, and it over-approximates the value function over here. And at x3, you're over-approximating over here, so the overall effect is something dotted that is above the true v of x. So you build up bias with this approach. You can still use it. It's just that if you iterate too many times, you're accumulating bias. Okay, that said, a good stopping criterion. How would you decide when to stop this algorithm? Any ideas? I'll give you a hint. Right. So at each iteration of this algorithm, you're computing a bunch of Q functions. Q for x of sample 1, Q of x for sample 2, up to Q of x for sample n. And you do this repeatedly, so iteration 2, you do different samples, but a bunch of them, until iteration whatever. Yeah, but so you have the hint I'm going to give you. You should use this data here somehow, the Qs that you evaluate. What do you think intuitively this average is going to look like? In the first few iterations, do you think it will be close to the true v of x? We don't have any optimality cuts yet, right? So it's a really greedy, stupid approach. It's going to be something that's probably going to be substantially higher than the true v of x. But eventually, as you're learning more about the value function, you're going to be getting cuts that are leading you to the right x. Hopefully, after a bunch of these iterations, you'll be around the true optimal x. So the idea is that once you've honed in on this true optimal x, you will be computing, and provided that your Monte Carlo sample is large enough, you will be computing an accurate approximation when you're doing the average of all these Qs. That will be an accurate approximation of the true v of x. So what you're basically going to keep an eye on is the variance of this estimator from iteration to iteration. you will look at its sample mean and make sure that it stabilizes somewhere, and when that happens, you're confident that your value function estimate here is accurate. Okay, that's the stopping criterion. You compute this guy, and when its variance stabilizes, you can stop. Does this deal with a small... I'm having real-time doubts about this criterion, for example, and my real-time doubt is, what if V is really small? I want to say that if you pick, V is a design parameter that you set in the offset of your algorithm. You fix it in your DAT file. So I want to say that if the V is really small to start with, the variance will never stabilize too much. So yeah, that's a real-time doubt I have about this approach, and you can agree, or if you have some counter-argument, I'm interested to hear it. Again, you could pick this V, like if you remember last time in the SDDP algorithm, we said, okay, if we wanted a guarantee that we are within 2% of optimal with a 5% probability, we use the central limit theorem to pick the number of samples we need to generate. So you could do some computation like that to pre-approximate the V and make it large enough. But anyway, moving on. Okay. Yeah, we have time. Okay, so that was the two of the three algorithms I wanted you to see. The third one is based on important sampling. So before I talk about the actual algorithm, I want to talk to you about important sampling. Have you seen important sampling before? No. Okay. So here's the idea. I'll show you the idea first of important sampling, and then explain to you how it applies in our case. And the idea of important sampling is to try and get away with more accurate estimates of average costs, or the average of a random variable, with fewer samples. So suppose that we are trying to estimate this random variable here. Think of it as the cost of operating the facility. If everything goes as expected for this facility, you get a daily cost of 1 unit, and that happens 90% of the time. But if something goes really wrong, the cost is 100 times bigger, but that just happens 1 out of 10 times. Okay? So you do the computations, the mean of this random variable is this much, the standard deviation is this much over here. How would you do a Monte Carlo simulation of this average cost? You write a routine in MATLAB, uniform 0, 1. If it lands underneath 0.1, it's a bad cost and you report 100. If it's between 0.1 and 1, you report 1. So then that's what I did, and here I'm drawing the moving average. The moving average is just this plot here is what you're seeing over there. Okay? What's characteristic about this simulation, about this approach, is that the rare outcome has an enormous impact on this average cost, right? It contributes by 10 out of 10.9 to the average cost. But how many simulations do we need to observe it approximately? How many simulations do we need to observe the rare outcome? Approximately 10. It's approximately 10. So just doing blindly Monte Carlo simulation, and now I could stretch this argument to an extreme, where something only happens 1 out of 10,000 days, and it contributes a lot to the average cost. So if you're just blindly running a Monte Carlo, you'll need to go through on average through 10,000 samples before you actually get some big news, some big information about the average cost you're computing. So the idea with importance sampling is that let's define a new distribution that puts more weight to these really influential outcomes. But now by changing our distribution, we've messed around with the data, so then the cost that we are sampling, we need to unbias them somehow. So here is what this looks like. If we're estimating expected cost, and this cost random variable is distributed according to a distribution f, Monte Carlo just uses this f, pulls the c's, and reports the average cost. What importance sampling does instead is it defines a new distribution G that pulls each sample with a likelihood that is equal to its contribution. This should be C of x here, sorry. This should be the probability of that xi times the cost of that xi, C of x. So it pulls out a sample with this probability here, and it unbiases the reported result by rescaling with f over g. Okay. Let's see how this. Okay, so how did we come up with this idea in the first place? We basically rewrote the expectation of the cost as this integral over here. So we just rescaled everything by this new distribution. So you can interpret the average cost that you are estimating as pulling stuff with a density f and reporting c, or pulling stuff with a density g and reporting c times f over g. So if you want to change the distribution of your simulations, you need to also rescale the results that you're reporting by f over g. Okay. Now, what I recommended using importance sampling was a specific G. It was this one over here. What is the variance of this random variable when I use this distribution here? What is the variance of this random variable when I use this distribution? The random variable that I will report, so again in the MATLAB script, now instead of just flipping and pulling according to f and reporting c, you should report c times f over g. So you'll need to define in MATLAB a new piece of data called distribution over samples and another distribution g over samples. And I want you to be reporting every time you flip a coin and observe a sample. I want you to report this random variable here. And this new distribution that I recommended for you to use for flipping the coin is given by this formula over here. So for a certain psi1, what will this number look like? Let's plug in the formula for G. What do we get? Right. How about for another psi2? So, great. Any psi you pull, you got the right answer in one shot. You can you do this? No, that's the question. The reason being the way we came up with G. But we did get an idea out of this approach. And the idea is to assign a weight to samples which is proportional to their contribution to expected cost, even if we don't know the expected cost. We can still apply this idea. We can come up with an approximation of the expected cost. In most problems that we're fairly familiar with, we know the expected cost within, say, like 50 to 150%. So we can come up with a number and pre-compute a new G based on this new density that we have. But the good thing with this new density is now putting more weight on important samples, hence the name importance sampling. Now, in our case, with the example of the facility and the cost that I showed you earlier, the new density, if we knew the expected cost, and actually for next year I should use a slightly different number here to make the point, but the new density for the normal day outcome, again, it's the chances of that outcome times its cost, so its contribution to the cost function divided by the average cost. So we get this new weight here. This is a new weight according to which we will pull out outcome 1. And the second outcome, which is the bad things happen outcome, gets much, much more likelihood in this new distribution. So instead of waiting 100 times to observe Xi2, with this new distribution here, we're more likely to observe, well, actually we're going to observe Xi2 10 times more often than we're going to observe Xi1. The problem is, if we did that and reported just C and averaged over C, we would be very pessimistic, right? So we need to unbias. Right, so if I re-weigh the distribution so that I see the important bad thing more often, and I just report C as my estimate of costs, that is a pessimistic estimate of the average cost. So the way you unbias it is by rescaling what you report by P over Xi, P over Q. And the guarantee you have is that this new estimate has an average cost which is exactly equal to the true one, but the variance is much smaller. Variance is much smaller means we need much fewer Monte Carlo samples to get the same answer. So that's the idea behind important sampling. Here's how we're going to apply the idea of importance sampling to our algorithm. The C, random variable that I referred to earlier in my example, in our case will be v of x, the value function given a decision x. So what we're going to do is what we need to apply the idea is the probability of pulling out a certain sample Xi and the cost impact given that sample. as well as an estimate of the average cost. So the ingredients we need to create a new G distribution, in our case, in the case of a stochastic program, are an estimate of the Q function for a given x and a given xi, as well as an estimate of the value function for that x. So then we just follow the same technique as in important sampling. The cost contribution for that outcome divided by the average cost. What's changed is that we are using estimates of Q and of V in our case. In the case of the estimation example I showed you earlier, the C of xi, you could argue we could, actually not even in that case could you really pre-compute it if you were doing, you would, yeah, it's pretty similar actually to the case we saw earlier. For a huge problem with the multidimensional xi, even pre-computing this is not easy. So the situation is similar in the stochastic program. So the idea is we come up with this estimate of the Q function, we come up with an estimate of the V function, and we run, we pull out samples of xi according to this Q distribution. And so we come up with this Q distribution. Now, one question you could pose is, what if my estimate of this Q tilde here is messed up? It has nothing to do with the true cost. Think about coding this, right? When you're coding this algorithm, you don't have much of a specific idea of what your cost looks for a given x for a given sample. So one idea that was proposed by Jared Infanger, who became quite rich actually by applying this method in financial engineering, is you create sublinear approximations of the value functions. So one example that you'll see in the book is another formula here, where you're just making approximations of how you think your cost will depend on x in general terms, in broad terms. When I took a class, for example, with Benjamin Van Roy in Stanford, we did approximate dynamic programming. Again, there we had to intuitively come up with basis functions that described how we believe the cost of the optimization problem depends on each x decision we make. And you can argue that, you know, if basically, yeah, you can make some reasonable assumptions about basis functions that describe your Q, but they're never going to be spot on, right? So you can build this approximation of Q, and then you can average it over the different xi. And one concern you might have is this new density G, little q that you're defining, is it going to actually mess up your estimate of the V of x? Because if you mess up the estimate, you're going to mess up the cut, and you don't want to do that. And the answer is no, it's not going to mess it up. It might create a worse variance than if you had used Monte Carlo, but it's not going to mess up the estimate of the average cost. The reason is the following. When you are then using important sampling to estimate the V of x, you will report this as your observation of cost. You are now sampling over a distribution Q, so you're taking an expectation here over Q. But since you then solve the second stage optimization problem, you get to observe the true Q of x, xi. So you pull out a new xi using this Q distribution, but then you get to observe the true Q of x, xi. And this expectation here is exact. It's an exact approximation of V of x. So since you're doing an expectation over Q, the q's cancel out, and you're basically left with an expectation over b of the true q function. So even if you messed up your q distribution, the value function on average, the cut you're generating on average is at the correct height. Okay. Now, if your q is precise, it's a good approximation of the true cost, then the cut is exact. For example, in stochastic linear programming, these q's are basically hyperplanes, and the slope of these hyperplanes are the dual optimal multipliers. But you don't know the dual optimal multiplier before you do the sampling. That's the problem. So you need to come up with heuristic expressions for q. Okay, that's the idea of importance sampling applied to the L-shaped algorithm. And here's how you would do it in code. So you have, at a given iteration, the relaxed problem. You have an estimate of this q and how it depends on x. You generate your little q distribution. You sample out of that distribution a bunch of samples. And then you use the same recipe for an optimality cut that I showed you earlier for sample average approximation. You take the average of the subgradients, you use minus that as your capital E matrix, you compute the average value function and this thing here, and you use all of that as the little e vector on the right-hand side. And you keep track of this quantity here, and its variance is an indicator of termination. When this variance becomes small enough, when this thing stabilizes, you're happy you've converged. So schematically, first simulate. At each of these steps, you've pre-computed some q tilde, some approximation of q. You simulate something, you optimize during these simulations, and you generate a bunch of cuts here. And then you use the x out of this phase to compute a new distribution g for importance sampling. And then the sample you simulate here is based on this new distribution g, and this g will always change depending on the x you're sending in from the previous step. Okay, that's the idea. And you stop after you've generated a bunch of cuts and your and this quantity here has stabilized. That's the idea of importance sampling. And here's an application of these ideas on a specific problem. So the problem that we're looking at is based on the book. It's page 393. We have a two-stage stochastic program. The only source of uncertainty is on the right-hand side. We have two random variables that are independent, identically distributed in 0, 1. And our first stage decision comes in this way, and we're just optimizing second stage costs, so the y1s and y2s are auxiliary variables, right? If we can't meet this right-hand side using just y3, we use the auxiliary variables, which can send us arbitrarily high or low. Same for the second constraint. Now, in Monte Carlo, sequential Monte Carlo, what we do is we generate, and the results I'm going to show you are based on 500 Monte Carlo samples per iteration, 100 iterations. Okay. Also, the book uses importance sampling, and it uses the following formula for G. So the estimate of the book for a Q function, well, actually, yeah, here it's not even like that. This is the formula that they use for defining a new distribution G for important sampling. Question is, if I calculate a certain XS, can you compute this G of Xi? Sure. If I've told you, you can just create this as data before running the simulation. Then you pull out samples based on this new distribution. And hopefully, this new distribution is smarter in a way than just dumb Monte Carlo sampling, and you focus on the important samples that influence the optimization problem. That's the whole intuition behind important sampling, and here are the results. Okay, so what you're seeing here is the X vector. Note, this is a two-stage stochastic program, but the first stage has a single decision, X. It's a one-dimensional decision, so here's how it evolves from iteration to iteration. The dark line is the true optimum, so it's something around 0.415, something like that. The crude Monte Carlo is a light gray line, and the important sampling-based solution is the dashed line. Here's a couple of things to observe. Well, both algorithms suck at the beginning, right? That's inevitable with L-shaped inspired methods. Then they kind of cross over the optimal. They're still looking for information to build a value function, so they hit it, but they're close to it, but they go through it, and eventually they stabilize somewhere around here. And it turns out that the important sampling algorithm stabilizes around 40 iterations over here, whereas the Monte Carlo is still looking for information because it's picking samples in a dumb way. Is the argument here. Here's a really interesting event. At iteration approximately 80, important sampling moves away from the true optimum. Based on what I told you earlier, can you justify why this might happen?
The bias?
Exactly, the bias. You're crowding your value function. You're crowding your value function estimate here. This is not only a problem with a sequential algorithm that uses Monte Carlo, it's also a problem for one that uses one important sample. It's the same issue. You are, as your iterations are going on and on, this thing is getting worse and worse. Unlikely, but it will happen eventually after many, many iterations. So that confuses, basically, the algorithm moves it away from the optimal text. So that's what you observe here. Yes?
So does the algorithm agree?
No guarantees. Okay. Definitely no guarantee of optimal solution. Absolutely not. But it's practical in a sense, right? And you get an answer here from your optimization problem. And okay, so that's the x, and here is the value function. So this is the objective function of the problem. The true again is the solid dark line. And what do you observe here for the two methods? It's quite striking. Right. Right, exactly. So indeed, the variance of the important sampling approach is much, much smaller. That was the whole motivation. Again, if your G is lousy, it's just gonna hurt the variance. It's not gonna hurt your estimate of the value function. Okay, important to realize. Now, I don't know if Matthew will choose to do this tomorrow, but I ended up implementing this too. So I have some code that I'm going to give you. Now, I have a few doubts about whether everything is fine with the code, because I kind of got, yeah, I basically got this. This is the sample average, sorry, the moving average of the two approaches. So the green is the true optimum. I've changed the data a bit. So I told you in the book it's uniform 0, 1. Here I've discretized it into 10 bins. So it's a discrete distribution, so I could create input for ample. And so it's a slightly different problem, but it's almost the same problem. And this is the objective function value. So the moving average of the Monte Carlo, what bothers me here a lot. I mean, I like the fact that there's some variance in Monte Carlo and it's more than important sampling, but what I would expect intuitively is important sampling should be much faster at discovering the true average. So there might be, I mean, at least it's going in the right level eventually, so the algorithm is not complete garbage, the code is not complete garbage, but I'm having doubts about whether everything is okay with the code. So in case Matthew covers this tomorrow, it might be an interesting exercise for you to see under the hood how this algorithm works. Okay, that said, last thing I'm going to talk about today is scenario selection. So this is another way of dealing with large size of stochastic programs. And here the philosophy is that we, instead, when we have an enormous set of uncertainty, in the case of your project, basically it's not even a finite set of uncertainty. You have a time series model that can spit out an infinite number of outcomes. One approach is pick a few representative scenarios. So question immediately becomes which ones to pick, what weight to assign to them. And both of these things matter if you think about it. Sample average approximation, in a way, is a scenario selection algorithm. The first algorithm I showed you today is a scenario selection algorithm that picks little v out scenarios as representative ones and assigns the same weight to each of them. The argument is you can do this a bit smarter than that. This is an idea that we had with my advisor, and we published it in operations research, inspired by importance sampling. And the idea is the following. You solve an easy optimization problem, like a deterministic equivalent of the true stochastic program. That's just a single LP. It comes up with the first stage X decision. You apply it, you fix it, and you run a very large number of candidate scenarios, out of which you're just going to select a few. So, say you're going to select, so in our work we chose either 10 or 40, and the original set of candidates was thousands of win scenarios. And the idea is that based on the X you've computed for the deterministic equivalent problem, you will use the performance given that X as an estimate of the cost of that sample. That's not the true cost of that sample. The true cost of that sample is what would have happened if you were doing the optimal X in the first stage, not this heuristic X that we came up with. But if your deterministic equivalent problem is reasonably close to the true stochastic program, then it's not such a bad approximation. Okay, so the idea then is you compute this cost for a deterministic policy of each sample. You compute then an average cost, and you apply the important sampling idea to this large data set here that has thousands of win scenarios. You take these thousands of wind scenarios, you assign to them a new probability, which is the cost of that outcome, but an approximate cost, given the deterministic policy, divided by the average cost. And then once you've selected a certain scenario, you unbias it according to the most important sampling idea. So this does a couple of good things for you. For example, one of the things we observed when we were running stochastic programs on the California network is that days that had near zero wind for the full day could cripple your network. You were shedding load in the hours with big ramps, so you definitely somehow wanted to represent these samples in your input to the stochastic program. With the sample average approximation algorithm, you will probably yeah, I mean, actually, this is better illustrated with last week's present. With the project, actually. So, this, I can show you a real one that looks like this from California ISO. So these things happen. It's not just a time series model. It's based on real data. I think, yeah, I'll show you a real one in a bit. So with sample average approximation, maybe you end up picking something like this, which is pretty bad. It's unusually bad, but it's not the worst one. The red one over here, which is near zero for the entire day. You want that to be represented in your input. So you can use the important sampling idea. You can say, okay, let's make a first stage decision based on a heuristic method, the deterministic equivalent problem, and then compute the cost of this sample based on that lousy outcome. It's going to be a high cost. So in the new, when I'm selecting scenarios, I'm likely to pick out this really bad outcome. But then I unbias the selection by assigning a weight like this, which is exactly the formula taken from importance sampling. So that was the idea that we used. So instead of applying importance sampling to the L-shaped algorithm, we basically applied it to scenario selection. So these are thoughts you may want to apply in the project to control the dimensionality of your problem.